There, I'll officially start recording so I can capture this discussion about homework. Yep, there we go, should be there. So section 4, computational questions? And the words, yes. Do you have specific questions, or you just want to walk through it? Yeah, well, like, I don't have the actual numbers in here, but I can tell you what the logic would have been to answer them. So, yes, so just to orient us, this is homework 3 we're talking about. Everybody got it done on time, which means we can talk about it as a group. And as I was telling folks earlier, that happens about once every 5 years or so in my classes. So I'm celebrating the occasion, right? At this point, we had fixed effects of level 1. Let's see, what are my variables in the story here? Coping and stress, I think, is another one.
Anxiety is your prediction.
Yep, yeah, anxiety is the outcome. We added people coping and people stress and their corresponding contextual effects. And in section 4, we are adding how treatment type moderates the effect of person coping and site mean coping. So the first one would be a cross-level interaction between treatment as a site predictor and person coping as a level 1 predictor. And the second one would be a level 2 interaction between site mean coping at level 2 and treatment at level 2. So then we have the results of the model as well as effect size. So let me ask you this, which variance component should treatment by within site person coping have explained? At this point, your choices are random intercept, random coping slope, residual variance. Treatment by within site person coping. Does within site person coping have a random slope at this point? Does the other one? Actually, it should, it looks like. Yeah, after section 3, it has a random slope. So that would have been what it was. Had the interaction been between treatment and the other level 1 variable that didn't have a random slope, then it would be residual, because that would have made it a systematically varying effect instead. And if we have moderation of treatment by the between site coping effect or the contextual, yeah, that's going to explain random intercept variance at level 2. So in terms of the answers here, we want to know if the effect of coping was positive or negative. That depends on your results, positive or negative in A and B. Whether it was stronger in B than A, that depends on your results as well. And then trying to figure out which of the variances has been explained. So in these sorts of questions, 2 of them are automatically wrong. Can you tell me why? Yep, they're logically inconsistent. So for instance, level 1 random slope variance. You can stop reading right there because that's wrong. Random is level 2. So if you get to the level 2, then it's like level 2 slope variance for what as the term, and it has to be the level 1 slope that is random over level 2 units. So he's laughing. Word salad, right?
I'm just laughing at myself.
Yeah. Getting the words right is tricky. It's really, really tricky. And honestly, that's one of the giveaways when you see results that are maybe not correct, is that the words are a little sloppy because it's not specific enough. So I'm trying to drill down into exactly what these things mean, and it's easy to get it mixed up. So we have, for instance, this one. There's 2 of these that are impossible. Level 1 variation within sites is a possibility. Level 2 variation within sites is not. Level 2 is not within. Level 1 between is also a logical impossibility, and level 2 between would be a possibility. So I'm looking to help you practice those kinds of terminology as well. Last but not least, in terms of explaining variance, it's fixed slopes only according to this class. At least in terms of the way that I had you compute them, that would be the corresponding correct answer.
Is it possible that random slopes could do that, or is it minimal? Just curiosity.
So there are versions of R-squares that include random slope variance as explained. Those are known as conditional measures rather than marginal. So marginal means fixed effects only, conditional means adding in random effects. To me, that makes no sense. They exist though, because a random slope is an acknowledgement that the effect of a level 1 predictor varies across clusters. But I don't think you've explained anything by saying that. You've introduced a new kind of variance to be explained with cross-level interactions.
Okay, and that's,
So that's
no,
my-
no.
that's
I'm
my
not-
pitch.
I'm not complaining about answer, I was just inquiring.
Mhm.
I also saw where you said that the random slopes really shouldn't be changing the variance at all. In
Yeah.
one of the slides, I saw something.
Yeah, so
to that
you're
effect.
reallocating into another component, which is going to change the other ones. So for instance, if you have a random intercept only and you add a random slope, the random intercept then becomes conditional on the 0 value the random slope predictor is for. And so then it does mean something different, so you would expect the number to change as a consequence of that.
All right.
Yep. There are within the, there's an R-square MLM R package that Jason Reitz and Sonia Sturber made. It's demonstrated in example 2, I think. They have, if you read that paper and go through that package, they have versions of R-square you can request that have the random components in it. So they're sort of agnostic as to what is right. They just made a package that would make everything, and then you can choose to interpret as you wish. So that's another way of computing R-squares that would allow for that as a possibility. Did that help at all? This one, yep. Yeah, so treatment by within-site coping should have explained the level 2 slope variance for the effect of within-site coping. In that case, because there is a variance to be explained in a random slope. And if you see something that seems like it should have been right, I can always double check my answer key. As we've addressed before, I am imperfect. Sometimes I screw things up. And if you saw the SAS program that made this thing, you would be amazed that I haven't screwed up more. But fortunately, the TAs are on board to help me catch such things. They'll tell me if I screwed something up. So I feel pretty good that this should be right, but that doesn't mean that it necessarily is.
Non-homework question.
Yeah, non-homework question.
I was trying to find Glow et al. 2024
Oh.
for the reading.
Did I not? Where is that one at?
It's for it's on 11/6.
Oh, cross-classified stuff. Let me see.
Sorry, I was just trying to find.
Oh,
You
yeah.
have to go out to a site for it as opposed to it have been downloaded. Am I looking in the wrong spot? Or is it way? Oh, it's in the list way down there.
Yeah, this one I think I added after the fact and forgot to give it to you.
Oh, no worries.
So thank you for the prompt. I just read this the other day, actually. So again,
because you've done a very good job. I look at the files and I was like, it's not there. And of course, I didn't look at the list down below because that would make sense to look at the list down below.
yeah, I just added this one like recently and forgot to add the paper in. So I'll add that to Icon and send out an email with it as well.
Thank you.
But yep, because that's on the current topic. So good for you for trying to read. Exactly. That's good. So next up then, since everyone finished homework, is project check-in. So I have the check-in template that I would like for you to complete and upload to Icon. I also have the rubric for your presentation that I will complete and provide feedback to you. So this is a list of what I want.
Can we complete it for you?
Will?
Sorry,
I'm
joking, of course.
Yeah, I get you. Let me open it real quick because I did want to make a couple points about that. Let's see, what did I call that? There we go, rubric. Okay, so the point that I want to make is due dates. I need your presentations or links to where they are by noon. You will not be able to present from your laptops. I have a tech system here that has to remain in place. If you want to continue fussing with your presentation between noon and 12:30, then at least send me a link to where you can get it on SharePoint. You can keep working on it, right? I've had people do that before. That's fine. I just need to make sure that I've got something. And I also will download a copy so that I can look back at it afterward. You will be recorded. You're not going to be on YouTube. Okay? The reason that I'm recording is so that I can watch it back and assigning your grades as needed, and Each of you is going to be doing a peer review of another person's presentation, so for that person who's reviewing you, they might want to see something again. But what I will do is put together a separate YouTube playlist that is unlisted, meaning that if you have the link, you can get to the videos, but you can't find them on the internet. So this will just be a local, like, shared resource for that. In terms of expectation, 15 to 17 minutes for the presentation. I'm going to sit over there and give you a 5-minute warning and a 1-minute warning. And you will be docked points if you go over, because in life, that is the one thing you do not do in a presentation, is go outside your time. Even if the people who went in front of you took your time and you're left with 3 minutes and you got to make it work, you got to make it work. So keep that in mind. Like, shoot for maybe 14 minutes and then breathe more as you're talking and you'll hit the right time. And then we'll have time for discussion. What else was I going to say? Okay, in terms of the points, so note where the bulk of the points are here: analysis, results, and style. So this is not meant to be a typical conference presentation in which you would spend the bulk of your time setting up why the study is needed, sort of summarize the process of getting the results, and then tell the story of the results and talk about the theoretical implications. We're going to sort of take the 180 reverse of that, in that I want a short intro so that we can understand, like, what's your topic, just a little bit about it, a little bit about the data, enough to be able to understand it, and then the process that you followed. So all of the intermediate steps that would normally be glossed over on your way to the final answer belong in these presentations, because the point is for each of you to get another example of what it's like to do an analysis of multi-level data. What are the intermediate steps? What are the things that can go wrong, and how did you solve that problem? So if you get hit dead ends, like this model wouldn't converge, or this random slope was breaking it, like, this is part of the story that you would articulate to all of us.
That's what I was going to ask, if it was that or we just summarize our final.
Nope, it's not meant to be like the pretty, let's pretend everything worked perfectly and it took me 5 minutes to do all this. It's not meant to be that. It's meant to be, we're going to learn from each other's process, because things don't go as planned most of the time. I'm also looking for you to be able to convey your results in ways that regular folks would understand. So pictures, verbal descriptions that try to put things into as simple a terms as possible. Please do not put output in your presentations or tables of numbers. Try to find ways to convey that information otherwise. It's minimal tables of numbers, I would say. And then here's the rest of my guidelines in terms of presentation style and aesthetics. If you want to show up to office hours with a couple slides and ask me what I think, that's fine. This isn't meant to be like an exam. This is meant to be a process that you're allowed to get as much feedback and input as you wish. So any questions about what is expected for your final presentations? Mm-hmm. Yes, this is a much more specific audience in terms of, you can assume background knowledge. Like, you don't have to justify why you did a quantitative study instead of a qualitative study, right? We don't need to have focus on that. But yes, you're correct in that the details that you would normally sort of gloss over or not report are what we're interested in for this context. So kind of more like a teaching talk almost than a research talk, I would say, in intent. To make sure that no one is starting this the day before it's due, you're smiling, No one would ever do that, right? You've never seen that happen in a class before, I'm sure. Definitely not one of mine either. I have this outline that's basically designed to make sure that you have been in your data set and starting to run things. And for those of you who are working with real data, do not underestimate how long it takes to get the data set ready to use. That is 80% of the work. So this is, what I'm asking for is pretty straightforward. I just want like ICCs and stuff like that, because you'll have to have gone through the work to get the data ready to even get this much. So I have, basically I want a description, remind me what your variables are, a description of what kind of model you used, and then how much variance is due to each kind, and then that for outcomes and that for predictors, and then for models with predictors, what happened in the things you've examined so far. So this is just a loose structure. I was trying to think of like what would be helpful in terms of for me to see to make sure you're on the right track. If you want to make this more of a conversation, like if you want to paste in code and be like, does this look right to you? Or this is my output, do you see any convergence problems? Or like, if you want to do that kind of thing, that's completely fine. I just thought I'd throw this up as a structure to get some information to you as to where you are and what you need to be able to be successful. Okay? If this is late, I'm cutting off half the points, 3 points for being late, because it defeats the purpose otherwise. We are running close to out of time. So my intent is to get you feedback on these things before Thanksgiving break, and then presentations start right after. So there's not a lot of turnaround time. I'm going to try to get this done as fast as possible so that it's before Friday, but I will probably get them back to you in the order in which you're presenting, to be fair. So those of you who are going first, get feedback first, that kind of thing. But it shouldn't take too long to get through all 9. All right. As I mentioned over email, I put up a new example 5B. I'm not sure if we'll have time to go over it in class, but if not, I have a video that does most of it that I recorded from a workshop. So this is just extra resources. I think the only person who has data that work like this is Dan, though. So this one's for you. Yeah, but it's not an ordinal model, so you still got to figure out that part on your own. So, all right, questions? Am I forgetting anything? Okay, cool. How about we talk about cross models? Yay. So what did we start talking about last time that makes these models different? And here's some words that you can use in your response. Make this big. Slide 2 in lecture 5 here.
People can belong to more than one. Depending where your level 2 like clusters are, you could belong to more than just one level 2 cluster.
Exactly. People can belong to more than one level 2 cluster at the same time. And that could be the same kind of cluster, but you're in different ones of them. So you could go to school A and then go to school B, for instance. You could be seen by Dr. A and then by Dr. B. Or it could be the case that you have clustering due to, in our example, we're going to see which primary school you went to as well as which secondary school you went to, and potentially others as well. So that's the key idea, is when there's multiple kinds of level 2 memberships that you have to pay attention to. Good. Here's some more resources than what I have time to talk about. But just to throw one example out here, this is what's in all the clustered multi-level books as a token example. Kids, schools, and neighborhoods. So kids who live in the same neighborhood don't necessarily go to the same school. Kids who go to the same school don't necessarily live in the same neighborhood. So if you think about a nesting structure, we could say that kids are nested in schools. We could say that kids are nested in neighborhoods. But schools and neighborhoods are 2 separate orthogonal level 2 dimensions in this example. So we have 3 piles of variance, so to speak, that would then be predicted. So we have level 1 residual, we have level 2 between school, so a random intercept that allows school mean differences in whatever this outcome is, and level 2 between neighborhood, which allows mean differences between neighborhoods in whatever this outcome is. And so we can have predictors of each kind. So for instance, what type of school it is might matter. The mean socioeconomic status of the neighborhood might matter. And at the child level, so let's say something like a kid's measure of aptitude or personality or something might matter. However, what's the rule? If you do something at level 2, what do you need to do to it? If you do something at level 1, I'm giving away the answer. You gotta do it at level 2. How many level 2s do I have here? Yeah, 2. So I have a potential contextual effect of the average IQ in this example of kids from the same school. I have a separate contextual effect possible for kids from the same neighborhood. So two distinct kinds of smushing at a minimum in this type of sampling design. However, in the example that we're going to see, there's actually going to be a third. Because for the kids who live in the same neighborhood and go to the same school, their scores might be more related than those of kids who just go to the same school but don't live in the same neighborhood, and vice versa. So if you think about the idea of an extra correlation, if you share both nestings in common, that sets up the idea of a third level 2 variance component. That would be the crossing of these, the interaction term. And that would be a third contextual effect that can be possible here as well. So we'll see that today. Good times, huh? So if there is only one level 1 observation per combination of level 2 crossed unit, then you can't pull out this interaction term. It is the same thing as level 1 residual variance. So for example, if you have one response, or one trial as it tends to be called in experimental settings, per combination of subject and item. So Dan has this in her data, right? You have however many respondents, they each answered your question one time. Okay, so one response per pair. So in this case, the thing you're measuring is ChatGPT usage, something like the extent to which you use it to do various things. Okay, so do you think some teachers use ChatGPT more than other teachers? You're assuming? You're going to find out. So in that case, that would be mean differences across teachers, who are the subjects in her example. Then we have items varying in either, you can think of it as their difficulty or their severity. So for certain things, ChatGPT might be used more than to do other things. Like it might be used more for copy editing than it is for writing a lit review. God, I hope. No hallucinations. So then we have an item random intercept. That would be why are some items responded to differently on average than other items. And then the residual is the same thing as a subject by item interaction. After you control for which subject is giving the response and which item is being responded to, what is it about this unique pairing that makes them different than what you'd predict based on which subject, which item? That's error variance, that's level 1 residual. That would be considered subject by item in terms of like conceptually what that variance represents. If there's more than one observation though, then that interaction is separable. So if I have more than one kid from the same school and neighborhood, then I still would have school mean differences potentially as one random intercept, neighborhood mean differences as another, and school by neighborhood as a random interaction. That allows an extra correlation of students who have both sources of nesting in common, and then residual is separable with that. So this would be remaining differences of kids from the same groups. And random slopes. So we've learned up to this point that if you have a level 1 predictor, it can have a random slope over level 2 units. In this context, that means effects of people things can vary randomly across level 2 clusters. We're good with that, right? So in this design, if I have a slope for a kid characteristic, that's a level 1 predictor. It could vary randomly over level 2 schools. It could also vary over level 2 neighborhoods. So random level 1 slopes over both level 2s. And here's the crazy part. You can have a random slope of one level 2 dimensions predictor over the other level 2 dimension. So the extent to which school predictors capture school variance could vary across neighborhoods and vice versa. In the example 5b is based on this one of responses within subjects and within items. In this case, item slopes could vary over level 2 subjects. So essentially, the features of an item that make it more or less difficult, the extent to which that happens could vary across subjects. Ta-da! Perfectly timed.
You
I did, and that's in example 5B. So our job then is to try to think about the idea of contextual effects, meaning extra level 2 contributions beyond what's expected at level 1 for all possible level 2 crossed dimensions here. And this paper, which is the one that you were just mentioning, which I forgot to give you, talks about that in the context of, mostly in the context of one observation per cluster. And I reached out to the third author, who is the person who's behind all of this work, and they said they're working on other papers to talk about the other situations. So stay tuned, there'll be more coming. So, all right, I think that's a good place to pause. How are we doing so far, folks? Eh? Thumb check? No thumbs. Eh? All right, let's look at an example, because I think that will help, and the rest of this is a little bit different. So I've got example 5 here. This is a data set that was from the Hawks 2012 multi-level modeling textbook. I'm almost positive it's fake. There's exactly 1,000 students. And they have SES on a scale of 1 to 6, which, whatever. Exactly, it's fine, it's totally fine. Interestingly, within this data set, I found 2 or 3 coding errors that changed the way that people were allocated to groups. So the results in the textbook are probably a little bit different than this one, because I went through and fixed those first. But the story is that we have 9th grade academic achievement. Sounds like a nice, normally distributed outcome that we can make up. 1,000 level 1 children are nested within 50 level 2 primary schools, which I think is like elementary, and within 33 secondary schools, which I think is like high school. So essentially you can be grouped by where you currently are in 9th grade, and you are grouped by where you used to be up to that point. So we have predictors for whether the primary and secondary schools are denominational, which I think means religious. There's not a lot of information about that. Again, made up data, so let's go with it. And child socioeconomic status. So there's between 1 and 6 kids per unique combination, which means we have the potential for that random interaction crossing to show up. And I will note that in the textbook, he smushed everything together. There was just one fixed slope for student SES, and that was it. So I fixed that too. All right. So there's a lot of data manipulation steps that have to happen here to be able to get just descriptive information. Essentially what I'm going to do is aggregate up to the primary school level, get descriptives for that version of the data set, then go back to the child level, aggregate up to the secondary level, get descriptives for that data set, and then go to the unique combination of the two and get a third set of descriptives.
Question.
Yeah.
Assuming you did this in real life, okay?
One might.
Yeah, I'm not saying that one would, but I said someone, assuming one did.
Mhm.
What if your 9th grader attended elementary school not in any of the listed ones? Do you say bye-bye data? Do you call it missing data? Or do you lump them all together into an other category?
Yes.
Very good. Just make your own justification as to why you did whatever you did.
Those are your choices, and you would have to pick one of those.
Okay.
Yep, because if you think about nesting, like the rule is any row that's incomplete with respect to the variables in your analysis is dropped. The same is true if you don't know where they came from. I would say that if you could make a meaningful category out of missing, meaning wasn't in the district yet, and you're willing to lump all those kids together, then maybe calling that like school 300 or, like making up a thing to put them in. But that seems sort of tenuous. Like lumping randos with missing data together is usually not something people would do.
It was the best school ever.
Yeah, or you'll have to kick them out and be like, I didn't have information, so I couldn't use this child. Yep, there's not a good solution to that. Yeah, that's all I'll say about that. So that is the overall picture here is trying to get a sense as to how things vary across each kind of sampling dimension in turn. So our achievement outcome is from 3.9 to 9.9. SES is from 1 to 6 with a mean of about 4. So those will be useful for centering. And if I just look at the relationship between child SES and achievement in the original level 1 data set, it's a positive correlation of 0.17. So the two appear to be somewhat related. However, what am I going to say? This is your turn. It's like fill in the blank. Yeah, do I like this number? Do I want to report this number? Not without a caveat attached. Is this the within school relationship, the between school relationship, the between primary relationship? All of them at the same time. So yeah. Mostly within, because there's more kids than there are schools, but this again is supposed to represent all of them. So I would not believe this number per se. So then I have Stata code that does all these things with the descriptives, and I have R code on the next slide that does them all as well, but the descriptive tables are in the Stata section, so we can roll through those. Yeah, scrolly, sorry. I think I've walked through some of this code before. Stata folks, do you have questions on how this works? I think you're the Stata folk, and you're the sole representative. I'm actually not 100% sure how some of these commands works because sometimes they give me errors and I'm not sure why. But I think the gist of it is that if you want to create a summary data set, you have this preserve thing first, and then you can collapse the rows into one per whatever this ID variable is in here, get your descriptives, and then put it back to the original. So the sequencing here really matters, is the thing to watch out for. So there are my 50 primary schools, and it looks like there is some variability in primary school achievement. There is some variability in primary school average SES, and 60% of the schools have a value of 1 for being denominational, whatever that means. Then we have a school level correlation table. So it looks like just bivariately, schools that are denominational, whatever a 1 means, they're higher. Schools that have more money are a little bit higher non-significantly, and larger schools are a little bit lower non-significantly. So it looks like nothing's correlated at level 2. That's never going to happen in life, but that's a sign of a made-up data set if I've ever seen one. Here is the same thing for secondary schools, so there's only 33 of those. So 50 and 33 each for our level 2 dimensions. That's not a lot. This is relevant for Stata in particular. So it took me about 15 years of fighting with Stata to make these models work. And I couldn't figure out what I was doing wrong. And then I found Don Hedeker's code and I was like, oh, you're a dumbass. I got it now. So this is relevant in Stata because you have to trick it to do crossed models. And there's a different way of setting up the code based on which level 2 unit has more of the sample size. So this one having fewer is relevant to the story. But the same concerns are not relevant in R. It behaved as it should have. So Stata is not built to anticipate cross models, so you have to do a workaround is what's going to happen here. But in the secondary school data set, it looks like there's not a lot of strong relationships either. However, keep in mind we got 33. So our power to detect predictors related to secondary school characteristics is pretty limited. And then last but not least, the unique combination. So I had to first create a new ID variable that is a combination of the two primary and school secondary IDs. So I called that unique ID. I then did the same process. So PS stands for primary and secondary at the same time. Did the same thing here. So there are 652 unique combinations across the 33 by 50. So not the full set of possibilities, but a lot of them. And most of the sample is a unique person in terms of going the combination of schools they go to, but there's up to 6 kids who belong to the same set of 2. So that means that there is this chance for extra correlation for children who belong to the same 2 sets of clusters at the same time. It's possible for that to exist. Then we get into centering. So I have created 4 different slopes for SES. The child level 1 primary level 2, secondary level 2, and unique combination of primary and secondary at level 2. So this is going to become a with-in effect eventually, and these are going to carry 3 different kinds of contextual effects. We know what a contextual effect is, right? What is it again? I don't know what this one means. What's a contextual effect, conceptually? Unique contribution of the level 2 cluster after controlling for the level 1 version of whatever it is. So then if you think about it, it's like, if you have money, things are better. Yay, you. If you go to a primary school that has money, how much better are things for everybody at that school? If you go to a secondary school that has money, how much better are things for everyone at your school? And then if you have both that are high, that's a third kind of contextual effect. So that's what we're setting the stage up for. But a logical precursor to that is making sure that SES actually has variance across all these sources. So we're going to look at that as well. For the point of illustration, I made 3 different versions of the level 1 effect. So I centered it at one of the cluster means, I centered it at the other cluster mean, I centered it at the unique combination, and then I threw all of those variables into a correlation matrix at level 1. And what this shows is that only centering at the unique combination rendered the level 1 variable completely uncorrelated with each of the level 2 means and the unique combination mean. So if you want to fully split things into within and between, it has to be within this and within this and within this, like all at the same time. Totally within. That is not covered in the paper, by the way. So that was why I had to write the email and ask about it. But this is, data don't lie. So the backstory to this is there's a whole set of models that I did not give you, which is me playing around with the data to make sure I understand what these things are doing. So just know that I had to figure this out, okay? So if it seems confusing and you're not sure what to do, yes, there's a whole lot of that. All right, so here's the corresponding R code to do those things. I am using the add unit means function in this example combined with the unique function to create a level 2 specific data set of each kind. I did this trick that I think Jonathan gave me, because I don't remember how it works, to make a unique ID. So they're adding something to fill out the extra digits. The other way that I've done this before is I take the first ID and then I take the second ID and divide it by like 1,000 and add them together. So then the decimals carry information about the second one. That's another cheap and easy way to make a unique ID. I'm sure there's many other ways as well. So a lot more code than typical, but it all follows the same sort of pattern. We form the cluster means, look at them descriptively, and we have a separate data set for each of those things. And the centering and the centering and the correlations. Okay, are we ready to do this? We're here. 1A, empty means primary random intercept only. So the first place that I'm starting is, what is the effect of the cluster where you are right now? Is there a correlation of achievement outcomes from children who are in the same school currently in the 9th grade? That's what this model will be able to tell us. And you'll note the change in the notation. This looks different than usual for an equation, right? It's not been multi-levelified. This is what's known as a composite equation. In your presentations, you are allowed to write equations in whichever style you wish, or to convert them to more of a conceptual equation if it would be too ugly. So like your 3-level model equation is not going to fit on a slide. You're allowed to sort of like shortcut it in some way that makes sense. But this is an alternative. If you have a cross design, I think it's much more useful because then you have multiple level 2s. It's hard to figure out where stuff goes. But subscripts are even more important in this context. So CPS, this is not Child Protective Services. This is child within primary and secondary. So that's why I have 3 zeros here, because this is the starting point for all 3. And then I have U OPO, because this does vary over primary schools, but it's not varying over children or secondary. And then E gets a CPS as well, because this is per child within a primary, within a secondary. So the code up to this point is exactly what you've seen all semester. We have one random effect inside the parentheses in R, or after the bar in Stata. We get our intraclass correlation for ICC 1 and Renova for testing the likelihood ratio test. That shows up by default in Stata. Here is some R output for that. So just eyeballing this, does it look like there's variance across schools? I'd say so. 0.18 relative to 0.57. The intraclass correlation that comes from 0.17 divided by the sum of those two is 0.23. So we can say that this is the expected correlation of children who go to the same primary school. We can also say that proportionately, of all of the variance in achievement, it looks like 23% of it has to do with what school you go to in terms of your current school. We can talk about it either way. And is 0.23 greater than 0? Usually, but I know for sure right here. So 170 as my likelihood ratio test statistic. It needed to be 3.84 to be significant at the traditional alpha of 0.05 with 1 degree of freedom. TA, is it going to throw you a question? Reviewer 2 just wrote and they said, hey, this should be a mixture chi-square. Fix it. What are you going to tell them? It's big enough? What do you think, Vladimir? You think it's big enough? Yeah, Mubarak's nodding back there. You can be an honorary TA in the back since you've stationed yourself in the middle. Yeah, it's big enough. So the mixture chi-square thing is only relevant when you're on the fence, because technically speaking, this should be a mixture of degrees of freedom 0, which can't happen for a chi-square, and 1, because the variance does not have a symmetric sampling distribution. It's bounded at 0. So the chi-square degrees of freedom would be 0 in the instances in which the variance wants to go negative but can't. It's on the boundary. So the critical value for a mixture chi-square is 2.71. The critical value for a 1 degree of freedom chi-square is 3.84. At 170, yeah, it doesn't matter. Either way, we're keeping this thing. So if reviewer 2 ever argues with you, you're just being a little conservative by ignoring the mixture problem. But I can live with that, and so can you. So let's set up a crossed model. I took pity on you. See, I knew that it was November and I had to not play Where's Waldo, just show you what's new in the code. So I have OOS. So what does that mean? UOOS. It's a random something for the school. It's an intercept. What kind of school? Secondary. So yep, this is another level 2 random intercept. This is how the outcome varies across secondary schools on average. So this would be the deviation from what is predicted based on this fixed intercept. So now this fixed intercept is both the mean of the primary school means and the mean of the secondary school means. So it's like doubly in the middle. So you can think of these as each deviating from it. And these are uncorrelated, by the way. They're 2 separate sets of level 2 effects, random effects. Okay, so in R, I'll show you that real quick for point of comparison. This is very straightforward. You add another set of parentheses to your formula. Not in the same set. In the same set introduces a covariance between all the things in that set. We want a different set. So this is 1 random intercept for primary schools that remains from before, picking up 1 random intercept for secondary schools as the new term, whose variance we then are estimating. So it's super straightforward in R, and in Stata not so much. So here's what has to happen for a crossed model. there's this second bar, so it looks sort of parallel in structure, but then you have this thing right here. So the way that this code is interpreted is described in these spots. I'll point you towards that. It's essentially a workaround because cross models are not built into Stata, so people have had to figure out how to do this. And this notation allows it to happen. It's essentially like another set of, how do I phrase this? Variance components that are all held equal across secondary schools that introduces a source of correlation. It's hard to explain, and I didn't understand it until recently, and I kind of still don't. It's a workaround. Don Hedeker, thank you. That's what I'll say. Final answer. But this, by the way, I could not get to work for example 5B. I could not get the cross models to run. And in my textbook, the cross models stop running in that chapter real quick too. So there's some computational difficulties that Stata Mixed has that the other programs don't, and I don't really know why. It has to do with how they set up the algorithms. So cross models are going to be more trickier in Stata for sure. But in this case, it is, I have both sets of output in here since this is going to be our first example of a cross model. So this is going to be the variance across secondary schools in achievement means. This is the variance across primary schools in achievement means, and this is the within school of each type residual variance across kids. I did a likelihood ratio test to compare against the previous model, and that test statistic is 75. So that means, yes, we definitely want to keep the new term. In R, we get the same results. New addition for secondary school. I believe this should follow the same order that you write it here. Should. Not guaranteed, but should. Whereas in Stata, it actually, did it reverse it? Yeah, I think I reversed it to match. So this one will always be first regardless of how you write the order. I've learned that much. So likelihood ratio test for our new secondary term, also significant. So previously, we had, let me go back to what the results were before. We had residual variance of 0.58 and primary school variance of 0.18, 1858. Well, this is still about 1.8, but this went from 5.8 to 5.0. The reason is that we have split the residual out into a second level 2 dimension that is right here. So it's like variance cannot be created nor destroyed kind of idea. Like you start out with all the variance in one pile, and we pulled the primary school out of the pile, and now we just pulled the secondary school out as a separate thing. So if you add them all back together again, you should get a number that resembles what the original variance in the variable would look like, because conceptually we've just split it into 3 pieces. Now, how to get an intra-class correlation is another story. So I'm doing some additional computations here to be able to get that, because there is no ICC function that works anymore with cross models. You got to build it yourself. And the one that's in R is untransparent, and I wasn't sure what it was doing, so I recomputed it myself so I could figure out what it was doing. Untransparent is a word, right? It is now. Well, it sounds better than intransparent. I'm going to go with un. Okay, so finding all the right variances and adding them together, that's what we're doing here in Stata. In R, I'm doing the same thing as well. So I'm spitting out the variance output into this little table so I can work with it. So these are variances, these are standard deviations, and you can tell which is which based on the labeling here. So I created a new object in R that holds the total variance from this table. That's the sum of these 3 numbers. So that's what's happening in this line of code right here. That sum worked out to be 0.759. So in these kinds of designs, I would stay away from the term ICC to help your readers. What I would switch to is proportion of variance. Like of the piles, so much is this, so much is this, so much is this. That will be easier to follow. In some instances, those can be considered ICCs, but not necessarily. So I have these labeled as ICCs, but the way that I would talk about them is just proportions. So of, like, if you picture like a pie chart, you know, of the total, 23% has to do with what primary school, about 10% has to do with what secondary school, and the rest of this has to do with kids within each of those same two schools. So I can compute an expected correlation of children from the same primary but different secondary. That would just be the primary school intercept variance over the total, so that's 0.23. The ICC for children in the same secondary but different primaries would just be the secondary over the total, so that's the 10% there. And then what if they both have both in common? If a child goes to the same primary and secondary, then what is the expected correlation with another child who goes to the same common for both? And that's adding the two random intercepts back together again. So then their correlation is higher because they share the primary part and the secondary part. And those numbers are how I figured out down here what ICC was doing. So in the, I think it's performance package, there's a function ICC. If you do by group, then you get the proportion of variance due to each level 2 clustering. If you leave off by group, you get the total of the two. So that's what I figured out.
And it'll do 3 levels.
Oh, it does do 3 levels.
It does.
Yeah, you'll want to figure out exactly what it's calling ICC for those, because for 3-level models, there's at least 4 different versions of ICC that I can think of off the top of my head.
And I did have level 1 variance given to me.
Yeah. Well, so inter-class correlations are always ratios of variances. But what's on the top and what's on the bottom is completely up for grabs. So that term doesn't really help understand what you're saying, unless it's for this kind or for this kind. So we have 2 different kinds of random intercepts. That means we have 2 different kinds of confidence intervals. So I have code that computes random effect confidence intervals for primary schools for the intercept and for secondary schools. And here's what those ended up being. So note I have the fixed intercept as the center of both. And then this right here, what number is that supposed to be? That would go in here? This is the confidence interval for the intercept for primary schools, so what should that number be? Which variance? I got 3. That's why I'm asking. Primary intercept variance should go here. Secondary intercept variance should go here. So if you work through the math, it looks like there is a relatively more variation across primary schools than there is secondary schools in predicted mean achievement. Each of these then has an ICC2, reliability of that cluster mean. They are relatively high. So 0.87 and 0.82 for those, computed as shown here. Right, so that's not bad. Empty model, the switch is rather than talking about an intra-class correlation, we can talk about more than one, and it's easier to think about that as just proportion of variance rather than expected correlation necessarily. Now comes the fun part, OPS. Can we guess what that is? You're nodding, you're guessing.
It's the random intercept for the cross primary and secondary.
Yep, you can call this a random intercept interaction or random interaction, like that's the terminology I hear. And so yeah, this is there an extra correlation of kids who have both in common? That's what we're asking. So is it enough to know which school you go to for each of these kinds, or is there something special about going to both in common? So in Stata, I tried. Yeah, I'm like, it broke, so I quit, but it worked in SAS and R, so I went ahead and reported those results. So note, I have a third set of parentheses here for the random interaction. And again, why is this identified from the separately from the residual? When is this a logical possibility that I could pursue? What characteristics of this data set allow this to be possible?
Kids have more than one combination.
More than one kid in each unique combination.
Sorry.
Yep, more than one kid in each unique combination. So like in Dan's case, don't do this, okay? Like cross this off in your notes. This is not something you can do because you only have one answer per person and item. So it's that there's more than one case within each unique combination allows this model to be identified. That's why. However, it looks like there's not a whole lot there. So tiny number for the variance, relatively speaking. And likelihood ratio test is non-significant. But what about the mixture chi-square? Still non-significant. So. But what about power? Well, I got 652 unique units, so I think I got power. However, 60% of the kids have a unique combination. Like the combinations that have more than one kid are few and far between. So from that perspective, one could argue about power, but this is real data. So then in terms of expected relationships, I have 4 piles of variance now. And the new interaction term, random intercept interaction thing here, would be contributed to the intraclass correlation of kids from the same primary and secondary. So if you think of this kind of like ANOVA language, I have a main effect of primary, a main effect of secondary, and an interaction. It's what it is, but they're random terms, not fixed, but conceptually it's the same idea. Is there something special that happens when you put the two together that's not anticipatable? Is that a word?
It is now.
Anticipatable from the main effects. So the previous intraclass correlation for kids from the same pair was 0.334. After adding the random interaction to the model, it jumped up to 0.36. So said differently, these two numbers are the same. The expected correlation of kids from the same crossing is not significantly different by adding in this new random interaction variance. That's what the likelihood ratio test is going to indicate.
Or do you leave it in?
I took it out. It isn't needed. It will likely cause estimation problems as you move down the line. And Stata wouldn't do it at all, so I took it out. Those are my reasons. So now in terms of adding predictors, go back to this model here. This is where we're going to start from. Nope, not that one. I lied. This one. So how many piles of variance are in this model? Three. Level 1 differences among kids, level 2 differences among primary schools, level 2 differences among secondary schools. That means how many potential pseudo R-squares do we have to talk about? 3. So this is primary school random intercept. That's the idea. What kind of predictors would explain primary school random intercept variance? Say it again. Primary school characteristics for sure, and you had said
The kids.
the kid things. To the extent that child characteristics vary systematically across primary schools, that common variance can further explain primary school variance. What about this one? What kind of predictors explain secondary school random intercept variance? Yep, secondary school characteristics and commonalities of the kids from the same secondary school as a contextual effect, yep. And E, don't forget about E. It's leftover, but it's a special kind of leftover. What kind of predictors are going to explain E? Yeah, kid stuff, child characteristics. And if it's just within cluster centered, we would explain E. That would make these two go back up. So there's that same yoking in terms of explained variance.
Question.
Yeah.
Your notation, everybody has their own thing, I get it.
Mhm.
I also saw in a place where, since the primary and the secondary are on the same level, they chose to put parentheses around it to say that these are like grouped together
Mm.
and separated like the commas, saying that, these are my two different things, but they're at the same level. Is there a preference outside of just personal preference for doing that? Because I mean, I'm looking at this and I'm thinking, 3 levels, but it's not 3 levels, it's 2 levels, but it's.
So the question was like, should you use some parentheses to sort of delineate that this is nested in this or something like that?
So, something like that.
And did you say a comma?
That was in one of the,
Yeah, I think that if you really wanted to make the point that it's 2-level crossed and not 3-level, this could help with that, but so could words.
right, understood. I just,
So yeah, I keep it relatively straightforward. The only catch is just to make sure you keep these things in the same consistent order, because otherwise the system falls apart real quick. But yeah, notation is always a choice. Internally consistent is the most important thing. So, yep. There, put that back. Can we see like one model? You have an NU for 1? I think we do. It's only 136. I know. Contractually obligated, folks. Just keep that in mind. Did that one? Oh, hang on. Not 2B. That's too far. Oh, I know what I'm looking for. Sorry. Got it. Sorry. Buffering. The little wheel is spinning in my head while I catch up to what I'm looking for here. I know what I was looking for. More sound effects. SES. This is going to be our child predictor, right? The first thing we want to figure out for any predictor is where it can contribute. Does it have variance at level 1, each of the level 2s, and the crossing potentially? So I fit the same crossed model, including the random interaction, to SES as an outcome, so that I could examine the relative amounts of variance in it, so that I would know where to put it as a predictor. So I would recommend for any variable in a multi-level analysis to treat it as an outcome in an empty model, because that logically dictates where it can go and what it can do. And this is the greatest proof I can offer you that these data are fake.
Zero.
All the zeros.
That just doesn't happen.
It does not happen, and it really doesn't happen for SES. So there's no possible way. But he screwed up. A little bit of cross variance here, just a little tiny bit. So it looks like SES is entirely within at level 1 with a tiny bit at the crossing. Nevertheless, I am going to, in this example, go through what it would look like to add it properly if it were a predictor that has variance at both the level 2 units, because that's what's going to happen in life. So this result would indicate that it is not likely to have contextual effects at these levels because it does not vary at these levels. That is never going to happen to you. And by the way, this output looks okay until we get to this. Optimizer NL optrap convergence code 0. Okay, boundary singular fit, see help. I think it means it broke. Yeah, something broke. Yeah, and then I asked for ICCs, and I just got NA. Like, no, I'm not gonna. Nope, it just said no. And it looks like each of these variance components is non-significant, as one might expect, given their tiny, tiny values. So this result is telling us that SES was simulated to be an entirely within level variable. There, that was the one more model. Questions? So this is not so bad. Scratch? No, question. Scratch. All right. Do you want to go home 5 minutes early? Will that make you happier?
I can't go home.
No.
Surely.
You can just go wander around outside for
For
5
5
minutes and enjoy the lovely air. It's cold and windy. Yay. But it's not garbage day. It's Veterans Day. So think a veteran. All right. Let's see. Yes. Check-ins are next. Let us know if you need anything. Hope to see folks Thursday. Thanks for being here. Peace out.